Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives. So specifically today we're talking about local and absolute extremas. So let's go ahead and dive into it. Question of the day, what are local and absolute extremas? So I have an example right here. We have a beautiful function and it is just the minimums and the maximums. So when they're local, they're the general minimum and maximums. So let's go ahead and look at the general maximums we see here, or the local maximums. So there's a point right here, point right here. So the purple that we see are local maximums. Now let's go ahead and look for our local minimums. I have a local minimum right here, local minimum right here. So everywhere we see pink are local minimums. And then we have absolute extrema. So that's going to be the absolute minimum and the absolute maximum. So here, if I look for the absolute maximum, it's actually going to be on the endpoint right here. And then if we look for our absolute minimum, I'm actually going to say it's right here. So always what we do is we first identify any local extrema, and from the local extrema, we're able to extract the absolute extrema. So let's go ahead and dive into an example here. We want to find all the extrema of f of x on the given interval. So f of x equals x to the power of 4 minus 2x cubed, and we're on the interval -2 to 2. So our first step is always to find the first derivative. So we would say f prime of x is equal to 4x cubed minus 6x squared. I'm going to go ahead and try to simplify that a little bit because what we're trying to do is find the intervals of increasing and decreasing. So here I'm going to go ahead and factor out a 2x squared, and I'm left with 2x minus 3. Our second step is to set this equal to 0. So I set this equal to 0 and I solve for x. So what we're doing now is locating our critical points. So here when I set both of these equal to 0, I get two critical points. So I get one, x being 0, and then here I get x is equal to 3 halves. So our next step is to do our number line, right? And remember, we're not going to be going on forever. We're going to have endpoints. So we have an endpoint at -2 and +2. And I'm going to go ahead and fill in my critical points of 0 and 3 halves. And so I'm going to go ahead and fill in what this graph means, right? So what we do is we plug values into our first derivative. And if it's positive or negative, that tells us if our function is increasing or decreasing. So that means we need to take test points. So here we can choose any value in each interval as long as we don't choose the critical points. So I'm going to choose -1, +1, and now we need one between 3 halves and 2. I'll do 1 3/4, which is equal to what, 7/4? Alrighty, so remember, we need to go ahead and plug that back in to our derivative. And so that's why I wrote it out in my most simplified version possible, because that's what I'm going to go ahead and plug it into. So let's plug in -1. Here I got a negative value in this entire interval, which tells me my function is going to be decreasing. So now I'm going to go ahead and plug those into my other values. Here I have another negative value, so this interval is going to be negative, which means my function is going to be decreasing. Okay, we have one more. Okay, so I got a positive value here, positive, 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 and so that means my function will be increasing. So let's go ahead and talk about our local extrema. So of course we first identify if we have any minimums or maximums. If I look at my number line here, notice that on either side of 0, we're decreasing. That means it's not going to be either a local min or a local max because it does something like this where it evens out but keeps decreasing. So actually we get to ignore 0. It looks like at 3 halves, we have a local minimum because we can see we have a dip right here, right? We can see it goes from decreasing to increasing. So the values that we actually want to plug in are going to be x is equal to -2. We can skip x being equal to 0. X is equal to 3 halves. And now x is equal to 2. So right here, we for sure have a local minimum. And I'm going to make sure to write that out. We have a local min That's my shorthand way of writing it out. So we have a local minimum at x equals 3/2 because the first derivative changes from negative to positive. So now we're going to go ahead and identify our absolute extrema, and we're going to do that just by plugging in those values into the original function. So if we remember, f of x is equal to x to the 4th minus 2x cubed. So let's go ahead and plug in these values, and then from here we can see the largest value and the smallest value. Alrighty, so let's compare our values. First, we got a value of positive 32, which compared to negative 27 over 16 and 0 is going to give us our absolute maximum. So now we want to go ahead and look for absolute minimum, and of course it's going to be the only one with a negative value. So now we can write that out super fancy. I'm going to go ahead and do that. So let's go ahead and compare that in our actual graph. So I have it drawn out right here, and let's go ahead and look at this. So we talked about at x equals 0, we would have a little flat part, which we can see right here. It flattens out, but it's decreasing on either side, right? So we have it's decreasing, flattens out, and decreases again. And then right at x equals 3/2, we reach our absolute minimum. So this is at x equals 3/2, and then we increase again, right? Alrighty, let's go ahead and go through another example here. We want to find all the extrema of f of x on the given interval f of x equals x plus 1 to the 4/3 on negative 9 to 7. So remember, our first steps is to find the intervals of increasing and decreasing. Let's find our first derivative. When we do that, we're going to use power rule. So we get 4/3 x plus 1 to the 1/3. And now we need to multiply by the derivative of the inside because we're using chain rule. So the derivative of the inside in this case is just 1, which is nice. And we want to go ahead and set that equal to 0. So let's go ahead and do that. I'm going to divide 4/3 over, and I get x plus 1 to the 1/3 is equal to 0. If I cube both sides, right, that gets rid of that cube root. They cancel out, and so I'm left with x plus 1 is equal to 0. Subtracting 1 from both sides, I get x is equal to negative 1, and we found our critical point. So let's go ahead and draw our number line, and remember that we're bounded. So we have to include our bounds here. We go up to 7, and we start at negative 9, and we have a critical value at negative 1. So let's go ahead and find our test values that we want to plug in. Of course, on this side, I want to plug in 0. 0 is always super nice to plug in. And on this other side, I'm just going to go ahead and take negative 2. So let's go ahead and plug that into our derivative. I'm going to highlight it right here. So let's go ahead and plug in 0 first. And here I have a positive value, and that means my function is going to be increasing. So now let's go ahead and plug in our other value. And here I have a negative value. And so that tells me my function is going to be decreasing. So when we look at our local extrema, I can see that we have a local minimum at x equals negative 1 because our function our derivative goes from decreasing or negative to positive. And so we have a local minimum, and now we can plug in values to test our absolute extrema. And remember, when we test for absolute extrema, we need to include those endpoints. So let's go ahead and do that. So we can first look at our absolute minimum, and we can tell the smallest value here is going to be 0 between our other 16 and 16. And so now that we talked about this, 16 and 16 are the same values. So when they're the same value, they actually tell you that there's no absolute maximum. You cannot have two absolute maximums. There can only be one. So I'll go ahead and write that out. Okay, let's go ahead and compare this. So I have our graph written out right here. And now we can see that we do have an absolute minimum at 0. And that's going to be at x equals negative 1. And this also shows that our function switches from decreasing to increasing, right? And we do not have an absolute maximum because they're going to be the same on either side at all times, right? We have one more example here. We got some trig, everyone's favorite. So we want to find all extrema of f of x where f of x equals cosine squared on the interval 0 to pi. So I can go ahead and rewrite this. This is just going to be cosine of x to the power of 2. And so that tells me I'm actually going to use chain rule. So here my inside is just going to be cosine of x, and my outside g of u is going to be u to the power of 2. Now this helps me find the actual derivative. So f prime of x is going to be equal to u prime, negative sine of x, and I'm going to multiply that by 2u, but u is equal to cosine of x. And here we actually have a trig identity. And so this is going to be equal to negative sine of 2x. So I'm going to highlight this because it's our most simplified version. And we are going to go ahead and set that equal to 0 and solve. So I can divide both sides by negative 1. And now I can take inverse sine of both sides. The purpose of doing this is the inverse sine with the sine kind of cancels out and you're just left with the inside. So I get 2x is equal to the angle when sine is equal to 0. On the interval 0 to pi, so pi being right here, this is going to be pi over 2. Our function starts at 0, goes up to 1, and then goes back to 0. So we have two values where sine is going to be 0. So that's going to be 2x needs to be 0 or 2x needs to be pi. So solving for these two, I get x is equal to 0 and I get x is equal to pi over 2. So let's go ahead and fill in our number line. Okay, let's choose some test values. First, let's go to do pi over 4 and then perhaps 3 pi over 4. Here I got a negative value, negative, 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 and that tells me my function is going to be decreasing. Let's plug in our other value. And then here I get a positive value, so it's going to be positive, which means my function is going to be increasing. So here I can tell that I have a local minimum at pi over 2. And now we can go ahead and test for absolute extrema. So I'm going to plug all three of those values into the original function. Okay, from here we can find our absolute minimum and our absolute maximum. So looking at this, we can tell we have a minimum for sure right here at 0. However, if we look at our absolute maximum, we have two of the same exact values, which tells us there's actually no absolute maximum, right? Because we can't have two. Okay, let's go ahead and compare this with like the actual function. I have that drawn out right here, and voila. So we are bounded between 0 and pi, and we can see that we have an absolute minimum right here that we talked about, and so that would be at about pi over 2. However, we do have two of those maximums, which means we have no absolute maximum. They're the same value. And we also have that our function decreases, we hit our absolute minimum, and then we increase again. So that's all I have for us today. If you enjoyed this video, please make sure to check out the rest of them. I have the playlist linked down below. Otherwise, please give this video a thumbs up and comment other topics and problems you'd like to see done. Thanks for watching.